You know, for centuries, certain math problems have been considered just unsolvable. We've had to rely on approximations, on getting close enough. But what if there's a way to find the exact answer? Today, we're looking at a theorem that claims it can do just that, and it might just rewrite some fundamental rules of mathematics. Let's dive right in. And it's a really good question, isn't it? In a world that's built on absolute precision, from engineering spacecraft to running our financial systems, why do mathematicians so often have to settle for a good guess? That tension between a perfect answer and a good enough one is really at the heart of what we're exploring today.
So here's our roadmap. We're going to start by unpacking what makes polynomial equations so tricky. Then we'll look at why the old methods just don't quite cut it before we jump into this revolutionary new theorem. We'll break down how it works, walk through an example, and then, at the end, we'll talk about what this could all mean for the future of math.
All right, first stop, the world of polynomial equations. I mean, these things are everywhere. They're the building blocks for just about everything, from designing bridges to modeling economies. But, as we're about to see, getting them to give up their secrets with perfect accuracy can be, well, incredibly difficult.
So what are we really talking about? Think about equations where you have x raised to the power of 5, or 8, or even higher. Finding the exact value of x that makes that whole thing equal 0, that's called finding the root, has been a massive challenge for mathematicians for a very, very long time.
So, how have we dealt with these monster equations in the past? Well, for the most part, we've had to make a big compromise. We've had to choose approximation over certainty. You see, the classic approach uses things like Newton's method. These are basically super smart guess and check systems. They take a guess, see how close they are, and then make a better guess, getting closer and closer each time. But here's the catch. They often rely on computer calculations that can create tiny rounding errors. And worse, they can never truly guarantee a perfectly exact value. They just get you close enough.
And this is where our source material introduces a really radical idea. A theorem that suggests a completely different way forward, one that promises to leave all that approximation stuff in the dust. Now, listen to the confidence in that claim. Abel's impossibility theorem is a huge deal in modern algebra. It essentially proved that you can't create a universal formula to solve all polynomial equations of the 5th degree or higher. This new theorem, it basically walks up to that long-held belief and says, actually, I think I've found a way.
And this table just lays it all out, doesn't it? On one side, you have the old way, guessing, rounding errors, and no guarantees. But on the other side, this new theorem promises something totally different. Exact symbolic answers. It's built to avoid those errors from the get-go and deliver a precise, verifiable solution. The goal is shifting from close enough to exactly right.
Okay, so how on earth does it claim to do this? Well, it's described as a symbolic approach. Honestly, the best way to think about it is like building a complex Lego set. Instead of just trying to guess what the final model looks like, you follow the instructions, connecting one specific piece to the next until you have a perfect result. This theorem does the same thing, but with math.
Okay, I know. That formula looks like a total monster. But don't worry, we're not going to get bogged down in the symbols. The actual idea behind it is way simpler than it looks. It's basically just a recipe for calculating the different parts of the final answer, one step at a time.
Let's just break it down into 3 simple steps. First, you set up the problem using these special symbolic placeholders instead of numbers. Second, you use that big formula to calculate the value for each placeholder, using the value of the one you just figured out. This is what's called a recursive process. Kind of like those Russian nesting dolls, where each one fits perfectly inside the next. And finally, you put all those pieces together to get the exact answer. No guessing needed. So those different parts of the formula, they each have a specific job. The binomial coefficients are there to help manage the terms. The base coefficient keeps everything grounded in the original problem we're trying to solve, and the recursive terms are the engine, making sure each step builds correctly on the one before it. It's all just a very systematic way of building the answer. All right, theory's one thing, but let's actually see how this theorem works with a real example from the source material.
So, the source starts with a super simple problem. X minus 4 equals 0. Now, I know what you're thinking. Of course the answer is 4. But hold on. The point here isn't the answer itself. It's about watching how the theorem gets there without just solving it in our heads. This is the exact same process that could, in theory, be scaled up to solve way more complex equations.
Okay, so the step-by-step process gets applied. Those symbolic coefficients we were just talking about are calculated, one after the other. It's all building toward that final solution. And notice, there's no numerical guessing or approximation happening at all. And after all those calculations are done, the process spits out this symbolic expression. In this simple case, it combines the number from our original problem, which was 4, with the final result of all that recursive math, which happened to be 0. And bam! There it is. The final exact root is 4. Again, the big takeaway isn't the number 4, it's that this answer was produced by a formal, piece-by-piece process that guarantees it's perfectly accurate. It wasn't estimated.
And this right here is the holy grail of this theorem, a symbolic solution. It's an answer that's mathematically pure, totally verifiable, and completely free of the guesswork and uncertainty that comes along with all those traditional methods.
So let's zoom out. What would an approach like this really mean if it holds up? Well, if you suddenly have a tool that can give you exact answers where you only had estimates before, that could fundamentally change how we tackle complex problems in just about every field of science and technology.
So let's just recap the big ideas here. We've seen that the old methods have their limits. They often have to settle for being close enough. But this theorem offers a completely different path, one that aims for exact symbolic answers. And in doing so, it challenges some really long-held beliefs about what's even possible in math. At the end of the day, the goal here is to replace estimation with certainty.
And that kind of leaves us with one last big question to chew on. If a fresh perspective can potentially crack problems that have stumped geniuses for centuries, what other things that we think are impossible today are really just waiting for someone somewhere to look at them in a completely new way? Maybe the next giant leap forward is just one new idea away.